In the summer of 1943, a team of German engineers gathered at the Kummersdorf proving ground, 25 kilometers south of Berlin. Before them sat an American tank, captured in the Tunisian desert 4 months earlier. The vehicle bore the scars of combat, dust still embedded in its tracks, paint scorched by desert sun, dents from small arms, fire pocking its hull. But when a technician climbed into the driver's seat and pressed the starter, the engine turned over on the first attempt. The Continental radial coughed once, then settled into a steady rumble. The German engineers exchanged glances. Their own Panthers and Tigers routinely broke down on the road march to the front. Transmissions failed. Final drives stripped. Engines overheated. Yet this American machine had survived more than 5,000 miles of combat operations across North Africa and still ran like it had just rolled off the assembly line. The senior engineer ordered a complete teardown. Every component would be examined, measured, and documented. What they found inside would challenge everything German tank designers believed about armored warfare. 6,000 miles away, in a factory outside Detroit, workers on the night shift were building another Sherman. They would finish it in less than a day. By the time the German engineers filed their report, American factories would have produced another 1,000 just like it. The Germans believed they had built the finest tanks in the world. The Americans were about to prove that the best tank was not the one that won battles. It was the one that showed up to fight them. The misjudgment began with a fundamental difference in philosophy that stretched back decades before the war. German engineering culture prized precision, complexity, and theoretical perfection. The nation that had produced Mercedes-Benz automobiles and Zeiss optics applied those same standards to weapons of war. Each tank was conceived as a masterwork, a synthesis of the most powerful gun, the thickest armor, and the most sophisticated fire control systems available. The Tiger tank embodied this approach. When it entered service in August 1942, it represented the most formidable armored vehicle on any battlefield. It weighed 57 tons, mounted the devastating 88mm gun derived from the legendary anti-aircraft weapon, and carried armor up to 100mm thick on its turret front, with a gun mantlet reaching 120mm. In a direct engagement, a Tiger could destroy any Allied tank at ranges exceeding 2,000 meters, while remaining nearly invulnerable to return fire. The Panther, which made its combat debut in July 1943, combined formidable firepower with improved mobility. Its high-velocity 75mm gun could penetrate 111mm of angled armor at 1,000 meters. Its sloped frontal armor, inspired by the Soviet T-34, provided protection equivalent to much thicker vertical plates. German engineers considered it the finest medium tank design of the war. These vehicles terrified Allied tank crews. American tankers called the Tiger the Monster. They spoke of watching their shells bounce harmlessly off its armor, while return fire tore through their Shermans like paper. The psychological impact of facing German heavy tanks contributed to a mythology that persists to this day. That German armor was vastly superior to anything the Allies could field. German engineers looked at the Sherman and saw a vehicle that violated every principle they held sacred. The American tank weighed only 33 tons. Its 75mm gun was adequate against older German tanks, like the Panzer III and Panzer IV, but struggled to penetrate the frontal armor of Panthers and Tigers at normal combat ranges. Its armor, ranging from 50 to 76mm depending on variant and production date, could be pierced by the standard German 75mm gun at combat ranges. The high silhouette made it easy to spot on the battlefield. On paper, the Sherman appeared outclassed in every category that mattered. This assessment was not unreasonable given the metrics German engineers used to evaluate tanks. German armor consistently won tactical engagements against Shermans throughout the war. A single Tiger commanded by a skilled crew could, and often did, destroy multiple American tanks before being neutralized. The kill ratios in individual battles frequently favoured German armour by margins of 3-1 or higher. Michael Wittmann, perhaps the most famous tank ace of the war, destroyed more than 130 enemy vehicles during his career, many of them Shermans. But the German analysis contained a fatal flaw. They measured the Sherman by the standards of tank versus tank combat. They did not measure it by the standards of industrial warfare. They counted guns and armour thickness. They did not count factory floor space and shipping capacity. They calculated penetration values. They did not calculate replacement rates. The tank that arrived at Kummersdorf had been captured near Zbytla, Tunisia, on February 22, 1943. It was an M4A1 variant with a cast hull, one of 134 built by Lima Locomotive Works in Ohio during July of 1942. Its United States Army registration number was 3067641. A reconnaissance patrol from Schwer Panzer, Abteilung 501, had found it abandoned but intact during the chaos of the Kasserine Pass offensive. American forces had retreated so quickly that they left equipment scattered across the desert. The Germans recognized the intelligence value of an intact enemy tank. They transported it 350 kilometers overland to Tunis, a journey that took 4.5 days over rough roads. Then they shipped it to Germany, where it received the military registration WH-05894-117 and the testing designation Versuchsfahrzeug No. 259. The Kummersdorf facility had been testing weapons for the German army since 1875. Its engineers had evaluated the first German tanks during the Great War, tested the early Panthers that would conquer France, and examined captured French, British, and Soviet equipment throughout the current conflict. They approached the Sherman with the systematic thoroughness that characterized German technical work. First came the static analysis. Engineers measured every armour plate and stenciled the thickness in millimeters directly onto the hull using white paint. They photographed the vehicle from every angle, documenting damage and wear patterns that revealed how the tank had been used in combat. They noted that the tracks showed substantial wear but remained functional, that the engine compartment was dusty but well maintained, that the gun showed signs of repeated firing but no excessive erosion. Then came the functional testing. The Germans drove the Sherman around the Kummersdorf proving ground for several days, subjecting it to the same trials they used to evaluate their own vehicles. The 1 kilometer hilly track tested suspension performance and engine endurance. Cross-country courses evaluated mobility in difficult terrain. Speed trials measured acceleration and maximum velocity. At every stage, the Sherman performed within its specifications despite thousands of miles of prior use. The ballistic tests produced results that confirmed German assumptions about the Sherman's vulnerability. Using armour plates of identical composition and thickness to the Sherman's hull and turret, German gunners determined penetration ranges for their standard anti-tank weapons. The 88mm gun on the Tiger could penetrate the Sherman's differential housing from 2100 meters and its turret front from 1800 meters. The Panther's high-velocity 75mm gun achieved similar results. German gunners could destroy Shermans at ranges where the American tank's own weapon posed little threat, but when the Germans tested the Sherman's upper glacis plate under realistic combat conditions, they discovered something unexpected. When the tank was angled 30 degrees from perpendicular, simulating a vehicle that was not facing its attacker directly, the compound angle created by combining the glacis slope with the horizontal rotation produced an effective armour thickness that exceeded 100mm. The Tiger's 88mm gun could not penetrate this surface at any range. Even the Panther's superior gun required the Sherman to be facing directly at it to achieve penetration of the upper hull. This finding did not change German tactical doctrine. Tank commanders were trained to maneuver for shots against enemy flanks and rear armour, regardless of the specific vehicle they faced. The Sherman's side and rear armour remained vulnerable, and the turret could be penetrated at typical combat ranges. But the glacis test hinted at something the German engineers had not fully appreciated. American designers had thought carefully about how tanks actually fought in combat, not just how they performed on specification sheets. The more significant discoveries came when the engineers examined the Sherman's mechanical systems. Here, the differences between German and American design philosophy became starkly apparent. The first surprise was the gyroscopic gun stabilizer. No German tank had anything like it. The Westinghouse system used a spinning gyroscope to sense the vertical movement of the tank and automatically adjusted the gun elevation to compensate. The gyro rotor spun at more than 12,000 revolutions per minute, providing a stable reference point regardless of what the hull was doing. Electric motors connected to the gun mount responded to signals from the gyroscope, keeping the barrel pointed at the same spot in space, even as the tank pitched over rough ground. A Sherman crew could engage targets while moving at 15 miles per hour with approximately 70% accuracy at ranges up to 300 yards. At longer ranges, accuracy decreased, but the ability to fire on the move still provided a significant advantage. German tanks had to stop to fire accurately. In the chaos of mobile warfare, the ability to shoot while advancing provided a tactical edge. A Sherman could advance under fire, engaging targets as it closed the distance, while a Panther or Tiger had to choose between shooting and moving. German engineers photographed the stabilizer mechanism and documented its components with characteristic precision. They identified the gyroscope housing, the elevation motor, the control unit, and the power supply. They traced the electrical connections and measured the response times. The mechanism required only 24-volt electrical power to operate, yet despite this detailed analysis, Germany never fielded an operational tank gun stabilizer during the war. The engineering resources and manufacturing capacity required to develop and produce such systems at scale were consumed by other priorities. The second surprise was the standardization of parts. The Sherman's designers had built interchangeability into the vehicle from the beginning, following principles that American industry had developed over decades of mass production. Any suspension bogie from any of the 11 American production facilities could be unbolted and fitted to any other Sherman. The same was true for road wheels, track links, drive sprockets, idler wheels, engines, transmissions, and virtually every other major component. This standardization extended beyond individual tanks to the entire fleet. A Sherman built by Chrysler in Detroit used the same parts as a Sherman built by Fisher in Grand Blanc, or Pressed Steel in Chicago, or Lima Locomotive in Ohio. Supply officers could requisition components without specifying which factory had built the vehicles they supported. Parts could be salvaged from destroyed tanks and used to repair damaged ones regardless of origin. A depot in France could receive shipments from any American factory and distribute them to any American unit without worrying about compatibility. The logistics implications were profound. Instead of tracking thousands of unique part numbers for each factory and production batch, American quartermasters managed a unified inventory. Instead of maintaining separate supply chains for each manufacturer, they maintained one system that served everyone. The simplification cascaded through every level of military organization, from depot to division to individual tank crew. German tank production followed a different model. Each manufacturer made components to their own specifications using their own tooling and their own interpretations of design drawings. A transmission from one factory might not fit a tank from another without modification. Even within a single production run, variations accumulated as designs were modified and improved based on combat experience and engineering refinements. A Tiger built in January might require different parts than a Tiger built in March. This created a logistics nightmare that worsened as the war continued and production became more dispersed to avoid Allied bombing. Spare parts for a specific tank variant might exist in a depot hundreds of kilometers away, while the vehicle sat immobilized for want of a single component. Supply officers had to track not just tank types, but production batches and manufacturing dates when requesting replacement parts. The third surprise was the ease of field repair. American designers had anticipated that tanks would break down under the stress of combat operations and that repairs would need to happen close to the front lines rather than in rear area workshops. They designed the Sherman so that major components could be removed and replaced by ordinary soldiers with basic tools. The transmission and final drive assembly bolted to the front hull in a configuration that allowed the entire unit to be removed by unbolting it from outside the vehicle. A field maintenance crew could extract a damaged transmission, install a replacement, and return the tank to service in a matter of hours. No cranes were required, no specialized equipment beyond standard military tools. The work could be done in a farmyard or forest clearing with the front lines just over the horizon. The Panther's transmission was buried deep within the hull, accessible only from inside the vehicle through cramped passages that made work difficult and slow. Replacing it required removing the turret, extracting the engine, and then working in confined spaces to disconnect and remove the transmission components. The process demanded specialized equipment, trained mechanics, and workshop facilities that existed only in rear areas. A Panther that threw a track or stripped a gear in the field might be out of action for days or weeks while waiting for recovery and repair. The Tiger was even worse. Its complexity meant that field repairs were often impossible. Damaged vehicles had to be towed back to major maintenance facilities, assuming recovery vehicles powerful enough to move a 57-ton tank were available. Standard German recovery vehicles could not handle the Tiger's weight. Special Berger Panther recovery tanks were developed, but these too suffered from mechanical problems. Many Tigers were lost, not to enemy fire, but to breakdowns that could not be repaired before advancing enemy forces overran their positions. The contrast in maintenance philosophy shaped the entire conduct of armored warfare. American units pushed forward knowing that broken tanks could be fixed and returned to action quickly. German units hesitated to advance too far from their repair facilities, knowing that breakdowns in forward areas might mean permanent loss of vehicles. The Sherman's reliability was not just a mechanical attribute, it was a tactical advantage that influenced every decision commanders made. The German engineers compiled their findings into a technical report that documented everything they had learned. They noted the Sherman's vulnerabilities accurately. The armor was thin by German standards. The gun was underpowered against modern German tanks. The high silhouette made it easy to spot and engage at long range. In a one-on-one engagement with a Tiger or Panther, the Sherman would likely lose. But buried in the technical details was a more troubling observation that the report's authors may not have fully appreciated. The Sherman was simple. The Sherman was reliable. The Sherman could be built by workers who had never seen a tank before, using parts that came from factories scattered across an entire continent. The Sherman could be shipped across an ocean, driven across a beach, and maintained by mechanics working in muddy fields with basic tools. The German engineers understood what this meant. They understood it, and they could do nothing about it. The production numbers told a story that gun caliber and armor thickness could not. American factories produced 49,324 Sherman tanks between 1942 and 1945. This total came from 11 different manufacturing facilities, each applying mass production techniques pioneered in the American automotive industry. The Chrysler Detroit tank arsenal led all producers with nearly 18,000 vehicles. This single facility told the story of American industrial mobilization in miniature. The site had been farmland in 1940. By 1942, it was the largest tank factory in the world, covering more than 1 million square feet of floor space. Workers who had built automobiles before the war learned to build tanks in weeks. The assembly line techniques pioneered by Detroit automakers translated directly to armored vehicle production. The arsenal operated around the clock in 3 shifts. Tanks moved down assembly lines just as cars had, with components added at each station until a completed vehicle rolled off the end. Raw steel entered one end of the factory. Finished. Shermans emerged from the other end at a rate that would have seemed impossible to German planners who thought in terms of skilled craftsmen building individual vehicles. This single facility outproduced the entire German tank industry in most years of the war. Fischer Tank Arsenal added more than 11,000 Shermans. Pressed Steel Car Company built over 8,000. American Locomotive produced 2,300. Ford Motor Company contributed nearly 1,700, despite focusing primarily on other war production. Lima Locomotive Works, Baldwin Locomotive Works, Pacific Car and Foundry, and Federal Machine and Welder rounded out the production network. Germany's response was constrained by industrial capacity, strategic bombing, and design choices that prioritized quality over quantity. Total Tiger I production from August 1942 through August 1944 amounted to approximately 1,350 vehicles, all from the Henschel factory in Kassel. When Allied bombers destroyed 95% of the Henschel plant's floor space in September and October 1944, Tiger II production was devastated. Fewer than 500 of these formidable vehicles were completed before the war ended. Panther production, spread across MAN, Daimler-Benz, and MNH, totaled roughly 6,000 tanks despite being Germany's priority program from 1943 onward. The Panzer IV, Germany's most numerous tank and the backbone of its armoured forces through most of the war, achieved production of approximately 8,500 vehicles from 3 manufacturing facilities. The arithmetic was devastating. For every Tiger Germany built, America built 37 Shermans. For every Panther, 8 Shermans rolled off American assembly lines. The Germans could win every tactical engagement by a factor of 3 to 1 and still be overwhelmed by the sheer volume of American production, even at exchange rates of 5 to 1, which German tankers rarely achieved consistently. The mathematics favoured the Americans. The cost differential compounded the problem. A Tiger I cost 250,800 Reichsmarks to produce, and early production vehicles before manufacturing efficiencies were achieved ran as high as 800,000 Reichsmarks. A Panther cost 117,100 Reichsmarks. A Panzer IV cost 103,462 Reichsmarks. A Sturmgeschütz III, the most economical German armoured vehicle, still cost 82,500 Reichsmarks. German industry expended enormous resources producing a small number of extremely capable vehicles, while American industry mass produced acceptable vehicles in quantities that defied comprehension. The resources consumed by one Tiger could have produced multiple Panzer IVs. The resources consumed by one Panther could have produced multiple Sturmgeschütz assault guns. But German military culture demanded the best, and the best was the enemy of enough. The strategic implications went beyond simple numbers. German tank losses were effectively permanent. Every Tiger destroyed represented months of factory production that could never be recovered. Every Panther lost in combat or to mechanical failure was irreplaceable given the constraints on German industry. American losses were temporary setbacks. Every Sherman destroyed was replaced by new production within weeks. The assembly lines never stopped. The ships kept coming across the Atlantic. The flow of new vehicles was relentless. This created a fundamental asymmetry in how the two sides could fight. Germany had to conserve its armour, using it carefully for decisive engagements where the odds favoured success. America could afford to use its armour aggressively, accepting losses that would have crippled German formations because replacements were always on the way. Albert Speer, who became Reich Minister of Armaments in February 1942 and dramatically increased German war production through rationalization and forced labor, later characterized the conflict as a contest between two systems of organization. Germany's approach, which Speer called overbred, demanded exacting requirements and small numbers of high-end, technologically advanced systems. America's approach relied on what Speer called the art of improvisation, producing vast quantities of equipment that was good enough to accomplish the mission even if it was not the best in any single category. The reliability gap proved more decisive than any difference in firepower or armor protection. German tanks were magnificent when they worked. The problem was, that they frequently did not work. The Panther made its combat debut at the Battle of Kursk in July 1943, the largest tank battle in history. German commanders had rushed the new tank into service despite warnings from engineers that production models had not been adequately tested. The High Command wanted Panthers at Kursk to exploit their technical advantages against Soviet armor. They got Panthers at Kursk. They did not get Panthers that could fight. The results validated every concern that engineers had raised. Contemporary German reports recorded the disaster in clinical terms. Before reaching the first preparation area, 50% of vehicles were inoperative. 2/3 of these failures involved engine breakdowns. The remaining third suffered transmission and steering failures. Panthers were breaking down on the road march to the battlefield, not in combat against Soviet tanks. Within a week of combat, over 180 Panthers had been reduced to approximately 40 functional tanks. The operational readiness rate stood at barely above 16%. The most technologically advanced tank in the German arsenal could not drive to the battlefield without breaking down. Soviet tankers destroyed some Panthers. German maintenance problems destroyed far more. The problems persisted throughout the war despite continuous engineering efforts to address them. Panther operational readiness rates in 1944, after more than a year of production refinements, averaged 54% across all fronts. Monthly rates showed gradual improvement as manufacturing matured. In February, only 37% of Panthers were combat ready. The rate climbed to 50% by April and reached 78% in May, before fluctuating through the summer and fall. At no point did Panther operational rates consistently exceed 80%. The Sherman, by contrast, achieved operational readiness rates approaching 85% under comparable conditions. American tank crews could count on their vehicles starting, running, and fighting when ordered into action. This reliability was not accidental. It resulted from design decisions that prioritized maintainability over maximum performance, from manufacturing processes that emphasized consistency over craftsmanship, from a logistics system designed to keep vehicles running rather than waiting for specialized repairs. Soviet evaluations of Lend-Lease Shermans confirmed American reliability data. The Soviet 6th Guards Tank Army, which operated M4A2 diesel Shermans alongside their own T-34s, determined that their American tanks had a service life of 2,000 to 2,500 kilometers, comparable to Soviet vehicles. Engines required inspection at approximately 100 operating hours and could run for 250 to 300 hours before requiring major maintenance. Soviet crews appreciated the Sherman's reliability, even as they noted its vulnerability to German guns. The consequences of unreliability multiplied across German armoured formations as the war continued, and maintenance resources grew scarce. A meeting of the Panzer Commission on January 23, 1945, documented the scope of the crisis in terms that revealed how desperate the situation had become. The assembled officers reported 370 defective Panther final drives awaiting repair or replacement. They reported 500 defective Panzer IV drives that had failed before the Eastern Offensive could begin. They reported roughly 100 Tiger failures of various types. These were not vehicles destroyed by enemy fire. These were vehicles abandoned because their own components failed. General Tomerley stated that an orderly utilization of tanks was simply impossible under these conditions. The troops, he said, lose their confidence and in some situations abandon the whole vehicle just because of this problem. German tank crews who should have been fighting the enemy were instead fighting their own equipment. Crews who should have had confidence in their machines learned to expect breakdowns and plan for them. The psychological impact of unreliability compounded the practical impact. The 101st SS Heavy Panzer Battalion illustrated the problem in microcosm. When alerted for deployment to Normandy on June 7, 1944, just one day after the Allied invasion, the battalion possessed 45 Tiger tanks, with 37 listed as operational. The road march from their assembly area near Beauvais to the combat zone around Villers-Bocage should have been routine, a movement of roughly 165 kilometers over French roads. Instead, mechanical breakdowns and Allied fighter-bomber attacks reduced the available force to approximately 6 vehicles by the time they reached the battle area on June 13th. Tigers broke down along the route, recovery vehicles struggled to tow the massive tanks. Air attacks destroyed or damaged vehicles that had stopped for repairs. An entire heavy tank battalion had been reduced to a handful of operational vehicles before firing a shot at the enemy. Michael Wittmann's famous action at Villers-Bocage on June 13th demonstrated what a skilled crew in a powerful tank could accomplish. In a matter of minutes, Wittmann's single Tiger destroyed more than a dozen British vehicles, including tanks, armoured cars, and carriers. The action became legendary, cited for decades as proof of German armoured superiority, but the larger context reveals the limitations of German doctrine. The 101st SS Heavy Panzer Battalion had 45 Tigers on paper. It had 6 in action. The remaining 39 were broken down, destroyed by air attack, or still struggling toward the front. Wittmann's brilliance could not compensate for systemic failures that left most of his battalion's combat power sitting uselessly along French roads. The Battle of Aricourt in September 1944 provided the most comprehensive test of Sherman versus Panther in sustained combat. This engagement in the Lorraine region of France became the largest American tank battle on the Western Front until the Battle of the Bulge 3 months later. The German 5th Panzer Army committed 262 tanks and assault guns to a counterattack aimed at stopping Patton's Third Army. The force included 107 Panthers, 75 Panzer IVs, and 80 assault guns. These were substantial numbers by late war standards. Opposing them was Combat Command A of the 4th Armoured Division, equipped with M4 Shermans and M18 Hellcat tank destroyers. The German forces suffered from crippling disadvantages that had nothing to do with their equipment specifications. The 111th and 113th Panzer Brigades had been formed only weeks before being committed to battle. The 113th was organised on September 4th, 1944, just 15 days before being thrown into action. Crews had shortened training schedules and demonstrated little proficiency in tactical manoeuvring. Many had never operated as units before. Some Panthers were still receiving final adjustments from factory representatives when the attack orders arrived. The 5th Panzer Army lacked integral reconnaissance units and was forced to advance blindly into American positions. The careful descriptions of standardized parts and field maintainability and simple, robust design, they documented something more troubling. They documented an approach to warfare that German industry could not match and German doctrine could not counter. The tank they examined that summer had survived more than 5,000 miles of combat operations. It had crossed an ocean on a transport ship, driven off a landing craft onto a North African beach, fought through mountain passes and desert valleys, and arrived at their proving ground still running. Their own Panthers struggled to complete a road march without breaking down. Their Tigers required specialized recovery vehicles and workshop facilities for routine maintenance. The German engineers filed their report and returned to their work, designing more sophisticated vehicles, with more powerful guns and thicker armor. They continued to believe that technical superiority would prevail in the end. They continued to believe this even as American factories produced another Sherman every few minutes, even as their own Panthers sat immobilized waiting for spare parts that never arrived, even as the tide of war turned irreversibly against them. The lesson of what happened at Kummersdorf should not be forgotten. The German misjudgment of the Sherman was not simply a failure of intelligence or analysis, it was a failure of imagination. German engineers looked at the American tank and saw what they expected to see, a crude machine unsuited for modern armoured warfare. They did not see what actually existed, a weapons system designed for industrial war, built by a nation that understood production and logistics as strategic factors equal to firepower and armour. This was the one thing about captured Shermans that German engineers could not believe. They could not believe that a nation would deliberately build a tank that was good enough rather than the best possible. They could not believe that reliability and maintainability mattered more than maximum combat performance. They could not believe that the simple approach would defeat the sophisticated one. Their entire engineering culture, their entire national identity, told them that excellence meant complexity and that complexity meant superiority. They were wrong about all of it. The factories that built Sherman tanks have mostly been converted to other purposes or demolished entirely. The workers who staffed them, the welders and machinists and assemblers who built a tank every few minutes around the clock, have passed into history. The war they helped win ended 8 decades ago, but the story matters because misjudgment still costs lives. Nations still underestimate their adversaries. Engineers still confuse specifications with capabilities. Leaders still believe that quality will inevitably defeat quantity without understanding that both are meaningless if your equipment does not work when you need it. The Sherman tank sits in museums around the world now, a relic of a war that reshaped the 20th century. Visitors walk past it and see an old machine from another era, smaller than they expected, simpler than they imagined. They do not see what German engineers saw when they examined their captured specimen at Kummersdorf. They do not see the factories that could build one every few minutes, running 3 shifts a day, 7 days a week. They do not see the supply chains that could deliver spare parts across oceans and continents to wherever they were needed. They do not see the maintenance crews that could return damaged vehicles to action in hours using standardized parts and basic tools. They do not see the training programs that could turn civilians into competent tank crews in weeks. They do not see the system, and it was the system, not the tank, that won the war. If you found this story as compelling as we did, please take a moment to like this video. It helps us share more forgotten stories from the Second World War. Subscribe to stay connected with these untold histories. Each one matters, each one deserves to be remembered, and we would love to hear from you. Leave a comment below telling us where you are watching from. Our community spans the globe, from veterans to history enthusiasts. You are part of something special here. Thank you for watching, and thank you for keeping these stories alive. Components could not support the additional weight. Commanders learned that disagreeing with decisions that had reached the Führer was career-ending at best and potentially fatal at worst. The honest assessments that might have corrected German tank design were suppressed in favor of reports that told leadership what it wanted to hear. Problems were minimized. Failures were attributed to factors beyond control. The systematic analysis of what was going wrong and why, which characterized American military institutions, was dangerous in a system where acknowledging problems could be interpreted as defeatism. The American system was chaotic by comparison. Different units developed different solutions to similar problems. Coordination between branches of service was imperfect. Arguments about doctrine and equipment continued throughout the war, but the chaos was productive. Ideas that worked survived and spread through the force. Ideas that failed were abandoned, without regard for whose reputation was attached to them. The organization as a whole became more effective even when individual components struggled. By the spring of 1945, the consequences of these different approaches had become undeniable. American armored divisions advanced across Germany with operational readiness rates that German commanders could only envy. Sherman tanks that broke down were repaired and returned to action within days. Spare parts flowed forward through a logistics system that functioned despite the chaos of mobile warfare. Replacement vehicles arrived from ports where ships delivered a continuous stream of new production. German tank formations had disintegrated under the weight of their own complexity. Vehicles that should have been fighting sat in repair depots, waiting for parts that would never arrive. Crews abandoned Panthers and Tigers not because of enemy fire, but because transmissions failed, or engines seized, or final drives stripped. The magnificent machines that were supposed to turn the tide of the war rusted in fields and forests across the Reich, monuments to a philosophy that prioritized the wrong things. The men who had dismissed American industrial capacity as propaganda watched American factories bury them under an avalanche of steel. The engineers who had scorned the Sherman as crude and underpowered saw their sophisticated designs fail, while the simple American tanks kept running. The generals who had counted on quality defeating quantity learned that quantity had a quality all its own. The Sherman was not the best tank of World War II by conventional measures. Its gun was adequate rather than exceptional. Its armor protected against some threats but not others. Its silhouette was higher than optimal for a combat vehicle. In a controlled test against a Tiger or Panther, with both vehicles at full operational capacity and equal crew quality, the Sherman would likely lose. But wars are not controlled tests. Wars are fought across continents and oceans by millions of people over years of sustained effort. Wars are won by nations that can build weapons faster than they lose them, ship them to the front faster than they are destroyed, keep them running through mechanical failures and combat damage, and replace crews faster than casualties deplete them. By these measures, the measures that actually determined victory, the Sherman was arguably the most effective tank of the war. The German engineers at Kummersdorf understood this, even if they could not admit it in official reports. Their technical documents noted the Sherman's weaknesses accurately and in detail, but between the lines, in outcome of a tank battle than the technical merits of the tanks themselves. The Panther was superior to the Sherman by every metric German engineers valued, but paper specifications did not fight at Aracourt. Undertrained crews in mechanically unreliable vehicles fought against experienced American tankers who understood their equipment and knew how to exploit their advantages. German officers who survived the war offered assessments that contradicted the mythology of German tank superiority. General Hasso von Manteuffel, who commanded the 5th Panzer Army during the Ardennes offensive and was one of Germany's most respected armoured warfare experts, provided extensive interviews to British military historian B. H. Liddell Hart after the war. Manteuffel emphasised that much more importance should be placed on the speed of the tank on the battlefield than was generally believed before and during the war. The ability to move quickly, to reposition faster than the enemy could react, to concentrate force at decisive points. These factors mattered as much as firepower and protection. Maneuverability, Manteuffel declared, develops into a weapon and often ranks equal to firepower and armor protection. This was precisely the principle American designers had embraced and German designers had rejected. The Sherman prioritized mobility and reliability over maximum combat power. It could go places German tanks could not go, stay running when German tanks broke down, and concentrate faster than German formations could respond. The Tiger and Panther prioritized firepower and protection, optimizing for the decisive engagement while neglecting the countless factors that determined whether tanks reached the battlefield ready to fight. Albert Speer himself acknowledged Sherman capabilities in his post-war memoir, Inside the Third Reich. Describing reports from the Italian front, where American armor operated in mountainous terrain that should have favored defenders, Speer wrote candidly about what German commanders observed. The Sherman climbs mountains our tank experts consider inaccessible to tanks, Speer recorded. One great advantage is that the Sherman has a very powerful motor in proportion to its weight. Its cross-country mobility on level ground is, as the 26th Panzer Division reports, definitely superior to that of our tanks. This was a remarkable admission from the man responsible for German war production. German tank experts had designed vehicles optimized for destroying enemy armor in direct combat. They had not designed vehicles that could keep pace with Shermans across the varied terrain of a continental war. American tanks went places German tanks could not follow. American tanks arrived at battles German tanks never reached. The institutional cultures that produced these different approaches proved as important as the tanks themselves. American military doctrine emphasized adaptability and continuous improvement. After-action reports from combat units flowed back to training establishments and design bureaus within weeks. Problems identified in the field were analyzed by engineers who revised specifications and modified production. The Sherman that rolled off assembly lines in 1944 incorporated hundreds of improvements based on combat experience in North Africa, Sicily, and Italy. German military culture had calcified around fixed doctrines and personal loyalties that discouraged honest assessment of problems. Initiative in questioning established approaches was discouraged. Failure to achieve assigned objectives was often fatal to careers. Engineers who identified fundamental problems with the Panther's transmission were told to find solutions, not to question design decisions that had been approved by senior officials and endorsed by the highest levels of the Reich. Hitler made this rigidity worse through constant interference in weapons development. He demanded changes to tank designs based on intuition rather than engineering analysis. He insisted on heavier armor and larger guns even when engineers warned that existing automotive commanders did not know where the Americans were, how strong they were, or how they were deployed. They attacked expecting to find scattered rear area units and instead encountered experienced armored formations that had been fighting since Normandy. American tactics exploited every German weakness. Shermans used their faster turret traverse to engage targets more quickly than Panthers could respond. The Sherman's turret could rotate a full 360 degrees in 15 seconds. The Panther required more than twice as long for the same rotation. In close combat, where fractions of seconds determined who fired first, this difference proved decisive. American crews fought from concealed defensive positions that negated the German advantage in long-range gunnery. Panthers and Tigers excelled at destroying enemy tanks at distances of 1,000 meters or more. But the rolling terrain around Aracourt offered few such sight lines. Combat took place at ranges of 300 to 500 meters, where the Sherman's gun could penetrate Panther side armor and where faster reaction times mattered more than superior optics. Morning fog on several days allowed American tanks to close to ranges where even frontal engagements favored the faster firing Sherman. German crews expecting to engage at long range suddenly found American tanks emerging from the mist at point-blank distance. Training and experience failed them. Faster American reactions succeeded. On September 19th, American Shermans flanked and destroyed 11 Panzers using fog as concealment. Captain Lamesson's C Company of the 37th Tank Battalion arrived at a defensive position on a ridgeline 3 minutes before 8 Panthers appeared from the mist. Those 3 minutes made the difference. Lamesson's tanks were positioned and ready. The German tanks were advancing blind. Lamesson's crews engaged immediately, knocking out 4 Panthers before the German crews could identify targets and return fire. The Americans then withdrew over the ridge, repositioned several hundred meters south, and reappeared to engage the surviving Panthers from a new angle. The remaining German tanks, already shaken by the loss of half their number, were destroyed in detail. The battle continued for 11 days as German forces made repeated attempts to break through American positions. Each attack followed a similar pattern. German tanks advanced without adequate reconnaissance. American forces detected them and prepared ambush positions. Combat occurred at ranges that negated German technical advantages. German losses mounted. When the battle ended on September 29th, German forces had lost 86 tanks confirmed destroyed and 114 damaged or broken down. Only 62 of the original 262 vehicles remained operational. American losses totaled 25 tanks and 7 tank destroyers, a fraction of German casualties. The aftermath revealed as much as the battle itself. American maintenance crews recovered damaged Shermans from the battlefield and returned many to service within days. German recovery efforts salvaged some vehicles but lacked the spare parts and workshop capacity to repair them quickly. The American force that had fought at Aracourt was back to full strength within 2 weeks. The German force that had attacked them never recovered. The lessons were clear to anyone willing to learn them. Superior equipment meant nothing if it could not be kept running. Tactical advantages meant nothing if units could not generate enough combat power to exploit them. The most powerful tank in the world was worthless if it sat in a repair depot while the enemy advanced. Military historians have cited Aracourt as demonstrating that crew quality and tactical training can be far more important factors in determining the outcome